So the topic for today is the scientific method. So the scientific method is an approach to problem solving, really in general, and it's what most of us do regularly in our lives anyway. These are some names who are sort of involved in giving credit for uh, coming up with a scientific method, but mostly these gentlemen were looking for a systematic approach to doing reliable science where the results would be objective. That is to say, if somebody else did your experiment, they would get your result also if, if you were doing it correctly. And the three names here are ones, if you sort of Google the scientific method and look in Wikipedia, you'll see these names come up, among others. These aren't the only ones. Uh, the first name, I'll say his whole name, Abu Ali al-Hasan ibn al-Haytham al-Basri. He's usually called the middle of that, Ibn al-Haytham. He lived from 965 to 1040 AD. He did a lot of work in optics. He was from Basra, which is now in Iraq. Um, he was prolific, produced a lot of scientific papers, had collaborators, um, and that's well, anyway, that's a reasonable summary. Francis Bacon was a scientist who was from London. Notice he lived about 500 years later, sort of in the Renaissance as well. Galileo, who was from Italy, lived in Italy. He was born in Pisa from 1564 to 1642. Usually, Galileo is referred to as the sort of the first scientist, but there's probably a lot of Western bias in that. But Galileo was particularly famous for having a lot of trouble going against what at the time was sort of popular thought, but it originated with the sort of the Greek scientists like Aristotle that had become sort of ingrained in academic pursuits in the previous 1500 years. Galileo thought a lot of their physics was wrong. He was correct, it was, and he got in a lot of trouble for contradicting it. And so he was looking for a systematic way to do science where he wouldn't get in trouble doing it. And so he sought, if you read the top line, he sought an approach to research that would provide objective and reliable results. He could write down what he did, the procedure he used, he could present his results, and then if you disagreed, you could do the experiment and see what you got. The scientific method always sounds sophisticated, but it's really not. It's what we all do when we problem solve, when we're doing our best work. So a summary of the scientific method is: you ask a question, then you gather data, then you formulate a scientific hypothesis, then you test your scientific hypothesis, and then based on the testings that you do, you might have to modify your scientific hypothesis, change it slightly or something, or you might have to scrap it completely and go back to step 3 and come up with a different one, right? If you cycle that a bunch of times, then you'll hopefully obtain a successful scientific hypothesis, which we might call a fact. At least it seems to be a fact at this point. And then, after you've done that, you might try to do further testing, even though maybe you're mostly done, or you might encourage your peers to test it by publishing it. If it's super successful, it might become something generally known, a law or a theory, and we'll talk a little bit about those as we go. And so we're just going to break this down a little bit. So let me go back up here and say we're just going to sort of walk through these steps of this, and I'll try to give a few examples as we go. And so we ask a question. This can be just a personal issue, problem you're trying to solve in your house, or it can be a highfalutin question, some kind of cosmic puzzle, right? And so I'm trying to give you a few examples of each. Why won't my car start when I turn the key, right? That's a problem we've all probably had at some point in our lives. A little more scientific one might be, why does the queen butterfly look so much like the monarch butterfly, right? In biology, I think they call that mimicry, right? There are advantages for the queen butterfly to look like the monarch butterfly. We can form a hypothesis about that. Why do the planets orbit the sun? Why do distant galaxies appear to be redshifted? We'll talk about redshifted down the road. but what it means is objects that are redshifted are moving away from you. And so the question is, why do we see that? Why is that what we see? Right, so these are all questions for which you could use the scientific method to solve, and I'm sort of arguing that you already know the scientific method. This is a procedure that we all do when we're problem solving. So step 2 was then gather data. So if you're answering sort of a house question about, why won't my car start, you might just check a few other things, right? Gather some data. Well, the radio won't come on, and the headlights maybe come on, but they're very dim, or some other things you might test. Similarly, if you're studying, why do planets orbit the sun, you might start gathering data about that. Well, it looks like they go around the sun in ellipses. It took us a long time to figure that out, and by us I mean humans. It was Johannes Kepler, a German, around a contemporary of Galileo, deduced these ellipse shapes. It looks like sort of like an oval, as the paths that planet followed from the data of a different scientist named Tycho Brahe. And we'll probably talk about those towards the end of the semester, those guys. Some planets also have nearly circular orbits, so that's some data. If you were trying to understand why the planets orbit the sun, you might gather other data. But those are some bits of data you could gather in trying to answer your question, right? And so now you want to formulate a scientific hypothesis. This was step 3. And you've all heard of hypothesis. A hypothesis is really just a guess. In sort of layperson's language, we might call it a theory. When scientists talk about theory, they're talking about something different. But a hypothesis is what we call it, it's a guess. A scientific hypothesis is special in that it's falsifiable. So this is an explanation to the question, but it's falsifiable. By falsifiable means capable of being proven false. So, I could say, I could just make something up and say, well, there's an invisible genie who runs around and moves the planets, and he's undetectable. And that's why they go in a circle. That's really not falsifiable, necessarily. And so we want to come up with statements that are falsifiable so that if my explanation is in fact incorrect, it can be proven incorrect. And so that's what we want in our hypotheses. And so one scientific hypothesis for why won't my car start is the battery is dead, right? This is clearly falsifiable, right? If I say the battery is dead, you could pull it out and put it on a battery tester and see if it's dead or not. Why do planets orbit the sun? Well, we could say there's an invisible gravitational force that has this formula, where d is the distance from the planet to the sun, m is the mass of the sun, m sub sun is the mass of the sun, m sub planet is the mass of the planet, and g is a gravitational constant. This is in fact Newton's law of universal gravitation, and when they were answering this question sort of theoretically using physics, it's what led to this equation. And so now we can test the scientific hypothesis, right? Well, why won't my car start? If my scientific hypothesis is this battery is dead, I can connect the battery of another car and see if my car starts now. That would, if I disconnect my battery and connect a different battery and my car starts, that's a pretty good indicator. Not completely conclusive, but a pretty good indicator that my battery was dead. Or I can just take the battery out and have a mechanic test the battery, right? Those would be things I could do to test my hypothesis. If, by the way, my car still won't start and I find my battery is not dead, right, then I would have to go back a few steps and come up with a different hypothesis. Maybe my alternator is out. Maybe I'm out of fuel. I could try different ideas like that, right? If my question is why do planets orbit the sun, and my argument is the force is F equals gmm over d squared, I could start using this formula to do calculations, right? I'm saying if my argument is the sun is exerting a force that has this formula, I could start making predictions based on this formula about what paths the planet should follow, and perhaps I could apply this to other objects, like maybe if the moon orbits the Earth, it should probably be following the same formula. And so instead of having the sun's mass here, I'd have the Earth's mass where it says M sun, and I'd have where it says M planet, I would have M moon, and I would have the Earth moon distance in this D. And then I could do calculations with that and see if that in fact explains what the moon is doing as it orbits the Earth. And so there are lots of ways I can test this formula. In fact, that's what happened. This formula was tested, and it turns out it produced these weird ellipses and these circles and all kinds of different shapes that we see when we study these objects. And so now I have a successful scientific hypothesis. Maybe I said the battery was dead, I took it to a mechanic, showed it was dead, and so now I have a fact on my hands, right? Similarly with this approach, why do the planets orbit the sun? I've come up with this hypothesis that it's this force. In fact, this force was tossed around in Newton's time a little while, and Newton finally used it and showed that this mathematical equation for a force produces elliptical orbits excuse me, for the planets. It also explains why an apple falls, or why the moon orbits the Earth, and all these other things if you just apply the mathematics as it's given in this equation. Well, then you can the next step would be you can encourage your peers to test your hypothesis. You might have concluded your battery's dead. This little analogy has probably run its course. I don't think you would ask your friend to test whether or not your battery is dead. By the time you got to the mechanic, that would be enough. But you might show, if you had the formula for the universal law of gravitation that Newton came up with, if gravity makes planets move in ellipses, maybe it should also explain the orbits of comets, right? So comets follow usually either parabolic, sometimes elliptical, but parabolic or even hyperbolic orbits. And so if it's the same force of gravity, it should explain the orbits of comets as well. In fact, it did. That was tested. The same gravity, as I was saying earlier, that explains planets moving around the sun should also work for the moon orbiting the Earth, or an apple falling, and so on. And so further testing can be done beyond just the scope of the question you were asking, which for this problem was why do planets orbit the sun. You can go beyond that and start explaining other things. Our sun orbits the center of the galaxy from the same gravitational force, and so on. You might formulate a more general theory, and this is where the word theory that scientists use shows to be different than the word theory that we use in sort of our layperson's language. This theory, this scientific sort of fact that you've developed, really falls into how all objects interact with one another through their mass. Not just planets and things that orbit them, or planets and things that follow them, but also just two people sitting in chairs near each other. It turns out exert a gravitational force on each other, and if you have sensitive enough instruments, you can actually measure them. You might fit the theory of gravitational forces into a broader collection of theories of all kinds of theories, like all kinds of forces, like electrical forces or magnetic forces, and so on. We also could use this force in the class of physics called Newton's theory of motion, which also includes Newton's 3 laws of motion. And so a theory is usually a broader set of statements or facts that are collectively related to some area of science. And so, whereas in common language we often use the word theory the way a scientist would use hypothesis, the word theory to a scientist is a collection of already successful scientific hypotheses, facts or laws that are all related to one particular area of science. And so that's a sort of a short description of the scientific method. It underlies all the areas of science we'll talk about in this course, and all of the scientists who do work in this, in whatever fields we're talking about, use the scientific method or some variant of that, close variant of that, to solve their problems in the same way you diagnose a problem with your car.